In this video, we're going to see how to find an inverse Laplace transform using a method called partial fractions that you may have seen in an integral calculus class. This method, can get somewhat complicated for various scenarios we might run across, but in this video, we're going to stick with a very simple example and see how this method works at its most basic level. So we have here a capital F of s, 1 over s squared plus s minus 2. And the question is, that we're asking, is what does little f of t look like? Okay, so what we're really doing is asking for the inverse Laplace transform of 1 over s squared plus s minus 2. Now, I've reproduced our table over here on the right. I left out the sine and cosine functions, but they wouldn't give us anything more than what we have to work with so far, really. So if you look at what we have, nothing in the table on the right-hand side really matches what we have here. So what we do is we look at our function, 1 over s squared plus s minus 2. We see that we can factor the denominator. It factors to s plus 2 times s minus 1. And so what we do is we assume that this came from two separate fractions. So I'm going to put capital A, which is an unknown constant, over s plus 2, plus capital B over s minus 1. So we assume that there's some A and B for which what you're seeing on the right-hand side here looks like our original left-hand side. And then what we do is we add these two fractions together to get a common, we get a common denominator and add them. So we have A times s minus 1 over s plus 2 times s minus 1. So I multiply the top and bottom of the first fraction by s minus 1. And then on the second fraction, we multiply top and bottom by s plus 2. And you can see now that we have a common denominator. So this is equal to, we have A times s minus 1 plus B times s plus 2 over s plus 2 times s minus 1. Now this final thing that we have, this last expression, is equal to all of the ones up above it. So in particular, let me go back up and set it equal to not the original, but the original where we factored the denominator. So s plus 2 and s minus 1. All right, so this is where we are now. And what we'd like to do is figure out what A and B are. So we've got two fractions here that they're equal to each other and both have the same denominator. So the only way those can be equal is if the numerators happen to be equal. So let me set the numerators equal. So I've got 1 equals A times s minus 1 plus B times s plus 2. And let me put a little dividing line here because we're kind of moving on to sort of a next step here. And so what we want to do is figure out what A and B are. And so what we'll do first is we'll let S equal 1. Now if you look up above, that doesn't look so good. If we look at all these things that we have up above here, above this red line, we have lots and lots of fractions that have s minus 1 in their denominators. And if s happened to have the value 1, then we'd have 0 in the denominator. So this appears to be a little bit fishy, but in fact, it turns out it works. It gives us what we want. So we won't worry about it. We'll put 1 in for s here. So when we do that, the left side is still 1. The A times s minus 1 will turn to 0, so that term's gone. And then we have B times 1 plus 2. And so that's 3B equals 1. And so b is 1/3. Then we can basically do the same thing, but the next time around we'll let s equal -2. And when we let s equal -2, what we get from our equation is 1 equals a times 2 minus 1. And then the b, whoops, it's supposed to be a -2, so -2 minus 1. And then where the b is, we'd have b times -2 plus +2, so that'd be 0b. So that goes away. And so what we have is -3a equals 1, or a equals -1/3. So this gives us our partial fraction, what we call the partial fraction decomposition. So 1 over s squared plus s minus 2 is equal to -1/3 over s, and let's look back up and make sure we get the right thing here. The a was over s plus 2. So it equals 1/3 over s plus 2, excuse me, -1/3, and then plus 1/3 over s minus 1. So let's go on to a new page, and we'll remember these things. The -1/3 is over the s plus 2, and 1/3 is over the s minus 1. So moving on, let's remember what our goal was. We had capital F of s equaled 1 over s squared plus s minus 2. And the question was, what is little f of t equal to? And what we found is that 1 over s squared plus s minus 2 was equal to -1/3 over s plus 2 plus +1/3 over s minus 1. So if we want to find little f of t is the inverse Laplace transform of capital F of s. So that's equal to the inverse Laplace transform of 1 over s squared plus s minus 2. But that's then the inverse Laplace transform of -1/3 over s plus 2 plus +1/3 over s minus 1. And now what we can do is we can take the inverse Laplace transform and distribute it to each part. So we can bring it here and here. We can also pull the -1/3 and 1/3 off of their respective fractions and bring them out past the inverse Laplace transform. So this turns into -1/3 inverse Laplace transform of 1 over s plus 2. And then plus 1/3 times the inverse Laplace transform of 1 over s minus 1. And let's remember where we have this s plus 2, let's remember that s plus 2 is really equal to s minus -2. And let's see, I'll use a blue pen, and up above, let me just reproduce what we want. Remember that when little f of t is e to the at, capital F of s is 1 over s minus a. So you can see that both of the things we have here that we're doing the inverse Laplace transform have this form, 1 over s minus a, at least if we think of s plus 2 as being the same as s minus -2. So then what we have is we've got -1/3. The inverse Laplace transform of 1 over s plus 2 is e to the minus 2t. And then we have plus 1/3. And the inverse Laplace transform of 1 over s minus 1 is just e to the 1t, or e to the t. So this is our little f of t for the capital F of s that we had to begin with. So that's an illustration of how the method of partial fractions is used to find inverse Laplace transforms.